Today we will discuss about how to make resistance measurement, because in real world we have to handle various signals, and some of them changing resistance to be measured, some of them changing capacitance to be measured, and some of them changing inductance to be measured, and so on. So, we will see how to make resistance measurement. So, resistance measurement will be our topic today. Now, this we have taken up because there are very many resistance sensors there. Like for example, we have temperature sensors, platinum thermometer, and so on. So, we have in temperature sensors we have a resistance measurement that involves actually PRT, platinum thermometer, then thermistors. So, change in resistance here give you temperature, and then similarly we have in position measurement we have resistance sensors. In position measurement we have resistance sensors. Similarly, for example, we have in weight measurement or in torque measurement, all these things we have for example, weight measurement we use here we use strain gauges. So, they are basically resistance sensors, strain measurement, strain gauges. There again resistance change is used to measure the weight or the strain and so on. Here in position measurement we use potentiometers, and the temperature sensor like that. We have very many resistance sensors are there. So, we will see how to make a signal conditioner for general resistance sensors. So, that means we divide this resistance measurement into 3 different regions. So, one is very low resistance measurement. That comes probably few milliohms to microohms level of resistance measurement. This is one range there we use. This is actually used mainly for research purpose. For example, change in resistance to be measured accurately, or you prepare some samples and then measure the resistance of that. There it comes a very low measurement. This example would be prepare some samples, sample resistance measurement. Like it will be more like a solid metal whose resistance to be measured. They come at a very low resistance value, and then the second type would be medium range resistance measurement. There will be medium range. So, you have a medium range resistance measurement. This comes in the range, for example, 1 ohm to probably something like 100K, that kind of resistance, like potentiometer used in the position measurement, platinum thermometer resistance measurement, or thermistors. All these things fall under this category. Then we have third type is very high resistance measurement. This may be going 100 kilo ohm up, maybe even 100 mega ohm or even more. This is more like insulation measurement and so on. This is another application where we have to measure the high value resistance accurately. So, we had seen that three types of actually measurement, very low resistance, and then medium range resistance measurement, and then high range resistance measurement, and each one needs a different technique, because what is applicable in high resistance measurement may not be good for medium range, and what is applicable for medium range resistance measurement may not be good for low range resistance measurement. So, we have to understand where the errors are coming, what type of circuit to be used for each case. That is what we will see now. Now, if you see the general method, if you look at the earlier day measurements, they are more or like they followed the Wheatstone bridge technique. So, let us see what was the advantage they had, what was the disadvantage they had, and see what is the lesson that we can learn from there, and how best we can use them, and what modification we have to do measurements in today's instrumentation world. So, for example, bridge based techniques, we will see the bridge based resistance measurement technique. In this method, basically what is done is they had a source of excitation, you have a source, and then they had these 4 resistances connected in the bridge form. The well known bridge, Wheatstone bridge, is the basic technique. So, you connect this, and then connect the excitation, and then you connect your galvanometer or detector here in this. Now, the basic if I have, for example, the whole idea is that if I have the resistances here R and R equal, then if this is V supply and the galvanometer, then we have a resistance here R, and this is unknown resistance. This is the unknown resistance. Now, if you look at the this circuit, basically it is a voltage divider circuit, because if I leave this galvanometer, then this applied voltage Vs, for example, the applied voltage Vs is basically divided by a factor of 2 by these two resistors. They are fixed resistance. So, you get, for example, if I have 10K and 10K, then if this is a if it is 1 volt supply is given, then I know this point will be at 0.5 volt with respect to ground. I take this is my reference point ground. So, this is basically a voltage divider, and this will be sitting at 0.5. Then assume that this unknown resistance value also equal to this, for example, this value is equal to this, then obviously this point also will be sitting at 0.5 volt, because these two resistance are equal. So, the whatever 1 voltage that is applied will half of that appear here. So, that means this is equal to this and this is equal to this, that is or it can be all the 4 also can be equal. In that case, you get here 0.5 volt, here 0.5 volt, then the voltage across the galvanometer is 0, and we call the bridge is balanced. Now, that means when bridge is balanced, then we can take the resistance value here is equal to here. So, that is at balance, we can unknown resistance equal to R at balance. Unknown resistance equal to R. This is the basic Wheatstone bridge. Now, why it is so popular? It is a very simple circuit, but then it is easier to measure also, that you can change this. If you want to know the value of this resistance, normally what is if it is unknown resistance, normally what is done is they will actually we keep this unknown resistance. So, I will put an unknown resistance, and then if I want to know the value of the resistance, I vary this. So, see, I vary this so that the bridge is balanced, so that the galvanometer shows no deflection. Then I will take this R is equal to unknown resistance. So, I will adjust R to get a null in the galvanometer, then I take this value equal to this value, and this is a celebrated bridge technique, and even today it is used. And the reason is this is the most accurate way of measuring the resistance than any other technique that exists even today, and no one can beat the accuracy of this measurement with any instrument, even whatever instrument that you have, you will not able to beat the accuracy that it gives. That is the beauty of this one. Unfortunately, the only drawback of this system is that somebody have to vary this resistance and watch for the balance, and that is not possible in today's automated world. That is the reason that this is not used, but this is the most accurate method one can think of. So, let us see why it is so accurate. Now, when they used this bridge, normally what they had done was that they used this resistance and this resistance, mostly Constantine wires, or they go for manganene wires. So, manganene wires, if used as a resistance element, manganene had very low temperature coefficient. That is, if I take a manganene wire and the temperature coefficient of manganene wire is only 10 ppm per degree C. So, mostly they use a manganene wire. So, the temperature coefficient of fixed resistors, say of the fixed resistors, is equal to 10 ppm per degree C. So, with temperature the resistance change is very small. First of all, that if the temperature changes, then the resistance drift is very small, and then they put both manganene wire. Even whatever drift that is there, this and this will equally drift all the time. So, at whatever temperature that I am making measurement, you will find this is always at 0.5 volt as long as this is 1 volt. Similarly, if this resistance also manganene wire and this has a very low drift, and then if I see if this is also assume that is a manganene wire only, we are assume that I am using this for some measurement and then use a manganene wire, then you find with temperature this point also not changing. Assume this is also manganene wire, this also manganene wire, this and this also manganene wire, then you will find whatever may be the temperature of these elements, this will be at 0.5, this will be 0.5 as long as this is 1 volt. So, if the room temperature changes, then the balance is not going to getting affected at all. So, as long as the actual resistance are not changing, there is no problem. With temperature, these resistances are equally, whatever change here, that same thing happening here, and here as well as here also same change occurring. You will find balance is not getting affected at all. In case if the supply voltage changes, that also will not affect the balance of the bridge, because instead of 1 volt, if it goes to 1.1, then this will go to 0.55 and this also will go to 0.55, and the difference will remain same. So, if I use all the elements of the same wire, probably ideally if that has a low temperature coefficient like manganese or Constantine, then you will find the temperature change, room temperature change will not affect the balance, and the reading accuracy is not affected. Similarly, the supply voltage change also will not affect the balance and will not affect the accuracy. So, you will get accurate measurement irrespective of room temperature change and the supply voltage change. So, bridge method gives high accuracy. In this case it is 1, because all resistors are having same temperature coefficient. Then the second one is supply voltage, the bridge excitation voltage, rather bridge excitation voltage voltage will not affect the balancing point. Because of these two reasons, the bridge method is very accurate. For example, if you want to make position measurement, for example, for position measurement, if potentiometer is used, then if I connect the bridge, that is what I do is I will take the bridge and then connect this, then I put here also these two are manganese resistance R1 and R1 are manganese resistance of equal value. Then I put the potentiometer whose depending on the position, the value is changing. This also I put a manganese wire only potentiometer. Then I have another resistance which is again a potentiometer, again a manganese resistance I put here. Now the galvanometer is put here. Now if the for example, if this is the position, depending upon the valve position, assume that the potentiometer is varying and the resistance value of this gives you the valve position. In that case, what I do, I will adjust this resistance R, to get a balance. Once the balance is obtained, this value is equal to this value. So I know the position value from this reading. Now the important point is that all of them have equal drift. So it has no effect, temperature has no effect on this, and then even if this voltage changes, the position is, the galvanometer value is not getting affected, balance is always balanced because it is a null method. And then the galvanometer error also has no effect, because even if the galvanometer is not calibrated or even if it has 100% error, since it is a null method, at 0 only we are seeing, and this galvanometer also has no effect. So that way the three effects, that is one, the effect due to the error due to the source, error due to the galvanometer, temperature change due to error resistance change due to the temperature, all three has no effect on the final measurement. That is why this method is so accurate. And even today, whatever method you follow, one cannot beat the accuracy of the bridge method that one can get. All our attempts are only moved towards this to get the accuracy that we can get from this bridge method. So even though this bridge method is so accurate and there is virtually there is no error and it is a celebrated technique, it cannot be used in today's instrumentation world, mainly because to know the value of this resistance, one have to manually vary this to get a balance, and in automated equipment that kind of arrangement is not practically possible. That is why this method is not used nowadays in automated measurements. Otherwise, in laboratory measurement, this is the most ideal thing that one can get, and it is also the cheapest way of making measurement. So because one need not have a highly sophisticated equipment, if this can have any amount of error, that error really does not matter, and the source also need not be a highly sophisticated source. even the variation here has no effect. So, obviously, this is the cheapest that one can think of. So, this is the bridge method that was there. Now, what is the technique that is used on today's world? Of course, there are drawbacks in this bridge method. The main drawback is the voltage that you get unbalanced. Suppose if you want to measure the resistance using the unbalanced voltage, then the bridge is not accurate, in the sense that if I try to see from this voltage what is the deviation of this resistance, that kind of measurement it is not suitable, and then this also gives a lot of error. All the errors what we have discussed, the error voltage here is first of all non-linear, and then the error voltage varies with the source and so on, all the errors that come in. So, only at balanced condition this gives you the most accurate result. So, one have to use, if you are using a bridge, it is accurate and then it is cheapest, but then one have to go only for a null method. That is the drawback of this system. Now, let us see what is the most of the current instrument, what technique they use to make measurement. The most popular technique is use of a constant current source. So, the constant current source, using constant current source make the resistance measurement. Current source based resistance. If you look at this technique, that is a constant current source based technique, it is done like this. That is, you use a constant current source you have, and then this gives you constant current and connect the resistance whose value to be measured. So, I have a constant current source, maybe it is a 1 milliampere current source, then this is the resistance R whose value to be measured. In that case, if I know the current is constant, so the voltage across this will be R into I. So, in this case R into 1 milliampere. So, for R is equals to 100 ohms, then you will end up I will be 1 milliamps. So, I is 1 milliampere, then the V actually comes out to be R 100 ohms, then I is equal to 1 milliampere, then you will get V as 100 milliohms. So, what by measuring the voltage across this one can calculate the resistance, because current is known and it is fixed. So, you can make this measurement as alternative, and this has advantage that there is no balancing is required. One just measures the voltage across this and then computes the resistance value. That computation can be done just by scaling, or if you have a processor based unit, actual computation also can be done. And this is also linear, unlike Wheatstone bridge technique, where the unbalanced voltage is not a linear thing. Unbalanced voltage is non-linear. So, this looks better from the measurement point of view, but then there are drawbacks in this. Now, we are depend upon this current source to get this voltage, but then this current we have to obtain this current source using a circuitry, and that current what we had fixed 1 milliampere, the may not be 1 milliampere at all the room temperatures, because the main problem in electronic circuit design is room temperature variation, because room temperature variation can make the circuit performance deteriorate. It can deviate from deviate from our design values. For example, I designed the circuit for 1 milliampere current, the current should be always 1 milliampere, but the current will not be 1 milliampere at different temperatures. Maybe at room temperature I would adjust it for 1 milliampere. When temperature goes up, this current may go up or come down, because the resistance and the capacitors, the operation amplifiers, all the whatever I am using or the reference voltage that I am using, all of them will change with temperature, and net result would be this current would be changing with temperature, and then the whatever measurement that we make may not be accurate. And also we will have to put some voltmeter here or some measuring circuit here to measure the voltage. This also will drift with temperature. So, net result is you will have error due to this current change, error due to the error in voltage measurement. This will make the measurement not very accurate. So, net point is, the net result is that the error in current or drift in constant current source, or drift in constant current source due to ambient temperature variation, due to ambient temperature variation. Makes the measurement less accurate. Then the second issue is error in voltage measurement. Also responsible for error. Responsible for inaccuracy. So, of course, if you want to make it then reliable, then one have to make sure that we design a constant current source, the constant current source which is not drifting. Of course, no one can make constant current source with zero drift. Similarly, we will have a voltmeter which has no error, and voltmeter also drifts with temperature. So, temperature will play a very significant error, and then usual calibration error, because what you have set 1 milliampere may not be correctly 1 milliampere, even if it is not changing with temperature, the 1 milliampere may be estimated wrongly. Similarly, voltmeter also will have a calibration error. So, all these things makes this system less accurate compared to our bridge method which we have discussed, where this problem is not there, no calibration error, there is no voltage drift error due to the voltage, even if the excitation voltage changes, there produces no effect at the null point. I hope now you understand why the bridge technique is still surviving in spite of such a modern development. The bridge is still surviving because it is the most accurate measurement that one can make. Now let us see what are other errors possible in resistance measurement. Take for example, we have a low resistance measurement. Take a low resistance measurement. Assume it is a few milliohm resistance range, few milliohms to few microohms. If you have this is the range of resistance that is to be measured, then what is the problem that one encounters in this kind of measurement? Now, in this kind of measurement, if I put a constant current source and then try to measure the resistance, then I put a constant current source, then I try to I connect the resistance here and then try to see the voltage across the resistance. I put this and try to see the voltmeter here, put the voltmeter and see this. So, this is a constant current source, and this is the resistance R to be measured. Now, in addition to the error due to the I and the error due to V, we have another error, that is the contact resistance, because we will be connecting this resistance to this through a wire. So, you will have a contact resistance, even if to make it small and to make it join this one, there will be a contact here. So, you will have a error due to this. So, there is a error at this resistance. Similarly, there is a error at this extra lens had come in. That means, you will be getting a voltage at this point that represents not only this resistance, that represents this plus this, and that is a error, and this error will be very high if you are actually, if the resistance value is very low. So, you have, we call contact resistance issues. So, when very low resistance, in very low resistance measurement, very low resistance measurement, we will get the issues like this. One, the contact resistance, is added to the real value. Then second, since it is not a null method, some small amount of current actually will be flowing to this, flowing through this, and that will give error, and that anyway we will leave it as a earlier calibration error. So, eventually if I use if I am making a very low resistance measurement, then the contact resistance adds to the problem, add to the resistance value. So, for low resistance, for very low values of resistance, very low R, the contact resistance can create contact resistance, can give large error. Now, this is a major issue. So, in the case of very low resistance measurement, one have to go for some alternate method to avoid this error. For this only, the celebrated method is 4 probe resistance measurement, 4 probe resistance measurement. This avoids basically the contact resistance problem, avoids contact resistance problem. So, it is suited, so it is highly suited for low resistance measurement. Very low resistance measurement. Now, let us see how this how this 4 probe method avoids this contact problem. Let us see how this 4 probe method is how the measurement is made using the 4 probe method. So, in 4 probe method, what is done is you have a current source. So, it is a DC source, then you set the current, say 1 milliampere. This current to be selected depending upon the resistance value, we come to that quickly. So, you have this, then connect, if you have, for example, if I have a long for example, I have a rod whose resistance to be measured. I take the rod, I put a silver paste and connect it here, then here also I put a silver paste and then connect this to this. So, we have here one probe here, the second probe is here. Then I connect the voltmeter not here, I will connect the voltmeter not at the end, then I connect the voltmeter, put a probe here and then make it make contact here, then make a contact here. So, third probe here and the fourth probe here. So, that is the voltmeter. Since there are 4 points here to our measurement, there is 1 point here, 1 point here to connect the current source. So, 1 and 2 connects the current source, and 3 and 4 probably we have at this point we put a wire, and need not be it can even be silver pasted or it can even make a contact, but good contact to be made with good mechanical contact also it can be made, or it can be even put a silver paste in permanent arrangement and connect that voltmeter which has a high resistance. Then now that means there are 4 probes now, 1, 2, 3, 4. So, there are we call 1 and 2 contacts, 4 probes 1 and 2 we call probes 1 and 2 are called current probes, current points. Probes 3 and 4, 3 and 4 are called voltage points. Now, so the idea here is that if I am passing the current here, you are passing the known current through this. So, this current is always constant irrespective of the value of the resistance. Now, the current that is flowing through that going to produce a voltage drop between this point and this point, because if this wire, assume that it is a thick rod, the volt resistance may be only few milliohms. Then whatever current that is flowing will produce a voltage drop between these 2 points, that voltage is read by the voltmeter. Now, the voltage at this point would be R into I. So, the voltage here is R into I. So, if I know the voltmeter reading, that is R into I, so voltmeter reading is equal to V, that is equal to R into I. Since I is known, R can be computed. Now, that is about the measurement, it is fine, but then the question is why there is this method is accurate, and then it is the contact resistance is not as a problem, because if you look at the circuit, the voltage that it is coming here only depends on the resistance between these 2 points, and this resistance and this resistance whatever is added because of the contact, that does not matter, because whatever may be the resistance, the current remain going to be constant only, because it is a constant current source. The current is always adjusted to 1 milliampere. So, this resistance and this resistance has no effect on the measurement. Now, there can be a contact resistance here and here, that also has no effect on the measurement, because the voltmeter has a very high impedance, the resistance of the voltmeter is so high for the resistance measurement. So, there will be a contact resistance at this point and this point. The contact resistance compared to the voltmeter resistance are very small. So, there is no error in voltage measurement also. Of course, the error of the voltmeter that will be there, but the connection, this connection produce a contact resistance, small contact resistance here, small contact resistance here, that actually does not matter, because that contact resistance is much smaller compared to the voltmeter resistance. Because of that, there is no error at this contact, there is no error at this contact. So, the measurement is accurate, you will be able to make a good measurement even if the resistance is few microohms or few milliohms. So, the contact resistance at the voltage probe, it does not matter. So, voltmeter reading is R can be computed. The contact resistance at the voltage points 3 and 4 will not affect the accuracy. This is because if you draw the equivalent circuit of the voltage measuring circuit, it looks like this. It is a voltage source with two contact resistors connected to the voltmeter. So, if you look at this, the contact resistance and the voltmeter. So, if the value wise, if I plot, if I draw the thing, it is like this. The contact resistance may be few milliohms or few may 0.1 volt, even 0.01 ohms, and this is 0.01 ohms the contact resistance, and the voltmeter resistance, if you see, equivalent circuit of the voltmeter resistance, that will be 100 megohm, that kind of resistance, because the voltmeter has a very high resistance. Now, if you see this is point, and if this is the voltage that is supposed to be measured, assume this voltage is 100 millivolt. This is the voltage drop that is generated across the two ends of the resistance, that is this voltage. This voltage to be measured. So, the contact rays are here, that is maybe 10 milliohm, and this is maybe 100 milliohm. So, now if you see the error, okay, the error in this circuit, this 0.01 ohm compared to 100 megohm is very small. So, all the 100 millivolt whatever is here appears here, and the error due to 0.01 ohm is almost negligible. If you compute and see, that makes no difference. So, because of this Power method is accurate. Of course, if you compare with the bridge technique, this is not nowhere accurate. Only thing is, if the resistance is very low value, then the Power method is good, because the contact resistance and the wire resistance, all these errors are gone. The error due to this current and the error due to the voltmeter, that still remains there. That error can be avoided only in the bridge technique, not in any other technique. So, the other error for low resistance, then the Power method is good, provided one takes care of this error due to this current and then error due to the voltmeter, which is normally not possible. So, you will have accuracy much less than the bridge technique only. However, for lower resistance, there is no other go other than using this 4-probe method. So, for all low resistance measurement, 4-probe technique is used. Now, let us see if I extend this technique, for example, for Platin resistance thermometer, which comes in the middle range, what is that I can do? Now, what I can do is the same constant current source I can put here. Then I can connect Platin resistance thermometer, say PRT. Then voltage across this will give me the PRT resistance and the corresponding temperature. If this is the current source I and this is R, that is R into I is the voltage output that comes across this. So, we get the voltage across this, which is actually proportional to the resistance value. In this case also, one can use a 4-probe method. For example, a Platin resistance thermometer in real life, it looks like this. You have a current source coming from instrument, and the Platin thermometer may be at long distance, may be inside the oven, whose temperature to be measured. So, we are put a long wire and then connect the Platin thermometer here. Now, if I measure the voltmeter reading, the voltage across this is nothing but voltage across this. So, if I see the voltage across this, that should give me R into I, if this is the I, but actually this long, if the resistance of the wire is long, then this resistance and then this wire resistance, that matters a lot. So, the true reading is at this point, the true reading is say at these 2 points A and B. So, the true reading is at this point, that means if I want to measure, I should take these 2 wires. And then put a measuring circuit here. So, this should have I impedance, this measuring unit should have I, like a voltmeter, this should have I impedance, then the wire, this wire impedance is not a problem. So, you will get a true reading of this resistance, then this wire resistance, this and this will not contribute for the error. So, this is also a 4 probe method, because you have 1, 2, 3, 4 probes are connected, and this gives you error without this wire resistance. This is how the Platon's thermometer is used to make measurement. Now, if you look at the current sources, we have different current sources that is used. We will see how what are the different current sources that is available, which one is suited, we can see quickly. Now, one problem is that whether this technique can it be used for high resistance, this medium range of resistance, this technique works well. Your low resistance, very low resistance also, this technique works all right. The medium range, even also we can also use a bridge if balancing is not an issue. But if it is high value resistance, for example, if it is 100 megohm resistance, then this technique is normally not favored because of the following reason. For example, if we use a constant current source, so high resistance measurement, high resistance measurement megohm or 10 megohm or 100 megohm resistance, high resistance measurement. For this, constant current source method is not suitable. Constant current source method, current source method not suitable, and it is not required. This is because we are constant current source mainly eliminates the connecting resistance and the contact resistance and so on, they are all very small. So, if you are measuring a 1 megohm resistance, and if the contact resistance and the connecting wire resistance are all few milliohm, the error that going to come in 100 megohm going to be very small. So, the contact resistance is not an issue. So, for high resistance measurement, constant current source method is not suitable. That is one issue. Then if I use a constant current source, what is the problem that we will face? For example, if I use a constant current source for very high resistance measurement, so the voltage that developed here is R into I. If the resistance is very high, then I have set only very small current of microampere per 1 megohm resistance. If I take 10 power 6 into current is 1 microamps, then you will get 1 volt. So, since the resistance if it is 100 megohm, then if I keep 1 microampere, I need at 100 volt. That means I should make a constant current source here, this one, which have 100 volt capacity. So, it is not possible to get that kind of voltage rating in the normal current sources. So, you have a problem soon, you will find if you want limit within few volts, then I have to only reduce the current I, the constant current that I am fixing, that is to be reduced, then only it is possible. So, constant current source method is not suitable because one is that we have to keep low current, and then that even if you achieve that, this resistance will have a leakage. For example, this source will have a ground voltage at one point. Now, there will be a leakage from the wire and all other things, there will be a leakage from this point to ground. Similarly, there will be a leakage from this point to ground. For example, if there is a leakage resistance from one resistance, for example, if you want trying to measure a voltage across one resistance like this, then I put this. If I assume this high resistance, very high resistance, then I put a constant current source. So, the constant current source consists of circuit which you will see now, that is one end is ground, assume that is this end, and then I connected this. So, we are trying to measure the voltage across this to get a field, to get the value of this. But then there will be a leakage resistance, the wire will have its own leakage, and the leakage current may be flowing like this. And this leakage also, if you are measuring 100 megohm, the leakage resistance also may be 100 megohm. So, what happens if I am sending 1 microampere current here, that 1 microampere current, part of them will be lost here to go through this, and whatever current that is flowing here is not 1 microampere, that will be less than 1 microampere, less by the current that is flowing through this. The current that is flowing through this is a loss, and that is actually not flowing through this. So, the leakage resistance makes that this current I, current through the sample is not the the current through the sample is not equal to the set current of the current meter because of this leakage resistance. So, we call it is R leakage. So, R leakage I write. So, because of the leakage current in the R leakage, the current flowing through this is not the set current. That means the voltage measured not going to be accurate. So, in high resistance, the leakage resistance leakage R leak diverts the current that is coming from constant current source. This makes the measurement less accurate. This makes the system this problem was not there when the resistance is high, mainly because if the resistance is this problem is not there when low resistance measurement. This is because at low resistance our actual current constant current source, whatever current we are sending from the constant current source will be high, and this resistance is small. When the resistance is low, then we can keep large current here and make this current also very small. So, this current will be negligible, and the leakage will not give much error in the case of low resistance. This problem comes only in the high resistance. So, that means what is the technique that we have to use for measuring the value of the high resistance, because we had seen for making a measurement with for low resistance we can use a 4 probe method, and then for intermediate frequency also we can use a 4 probe, intermediate resistance level also we can use a 4 probe method, but 4 probe method cannot be used for high resistance measurement because of the leakage current. Now, for high resistance measurement one can use the so called ratio transformer bridge for high resistance measurement. Use ratio transformer bridge. Now, what is this technique? How this avoids the error due to the leakage resistance? So, ratio transformer bridge looks like this. You have a AC source, that is connected to the transformer primary. Then it has secondary like this, and we have a tap secondary, it has a tap, and it is wound on a high mu core, very high mu core it is wound. Then I will put a, for example, I put a detector here, then I put one resistance, then another resistance here, and then I connect this to ground. This is the ratio transformer bridge. This is the resistance, I resistance, which is to be measured, R measured, and this is R reference. This is a fixed reference resistance, and that is to be fitted here, and this is the resistance which is to be measured, that is to be connected here. So, we have to measure the resistance R accurately using this, and this technique is very popular, and it measures the resistance, I resistance also accurately. Now, first thing is that this transformer, we have connected the primary to the AC source. So, you will have a induced voltage in this secondary. Whatever voltage you add, suppose if it is 1:1, then whatever voltage is put, that voltage will appear across this. So, if I take this, for example, this is primary and secondary. Now, for simplicity, assume that this is at the midpoint, then we know induced voltage here is V and here is V. So, the both voltages are equal. So, that means the first step would be that if the center tap, if the secondary center tap is at midpoint, then V1 equal to V2, that is, this is V1, say V1, this is V2. So, these two voltages, this voltage and this voltage are equal. So, if these two voltages are equal, and then we know that this voltage and this voltage are 180 degree out of phase, that means this will send a current like this, and then this will send a opposite current, that is, this current will come like this. So, current in this and this are opposite, that is, current in this will be like this and current in this will be like this. So, or other way around, the current due to this will be in one direction. If I look at here in this path detector, one current goes in this direction, another current is coming like this direction. If these two currents are equal, for example, if I keep here the middle, then V1 equal to V2, assume I put this value equal to this value, then these two currents also will be equal. So, the current that is going here will be then current that is coming here will be equal. The net result would be the current flowing through the detector would be 0, because this current and this current equal to this current. So, net current flowing through the detector would be 0. That means, if these two resistances are equal, and if these two and if it is at the midpoint, if it is the midpoint, automatically this voltage will be equal to this voltage, then you will get a 0. So, in that case, then I know that I had adjust this is at the midpoint. So, the bridge is balanced and it is showing 0, then I can take this resistance value equal to this resistance. If it is not equal, then one can adjust the center tap, that is, one can move this to balance the bridge. Normally, what is done is the unknown value is put here and the known reference value is put here, and the center tap is adjusted to get a 0. So, if you adjust 0, then the ratio of V1 V2 will give you the resistance ratio. So, this we will discuss more in the next class, and then also see how this avoids the leakage resistance problem to make the measurement accurate. Thank you.